Welcome back to my channel. Today I'm going to explain a recent paper called Ultra-Low-Bitrate Speech Coding with Pretrained Transformers. This paper is a collaboration between Georgia Tech, Chrome Media Google, and Victoria University of Wellington. So in this tutorial, I'm going to first cover the introduction of this paper. What is the main idea of this paper? Then we'll see what is self-supervised learning, which is very famous these days. Specifically, we are going to talk about something called Wave-to-Wake 2.0. Many people may be knowing about Wave-to-Wake, and I'm going to just explain Wave-to-Wake a little bit just to give you the context and make you understand how these self-supervised models are used in this paper. Then we'll see the transformer-based speech codec, how it is designed, and we'll see the training, and finally we'll see some experiments and results. So what is speech coding, or what is a speech codec? So speech coding is basically an idea or an algorithm which helps you transmit speech over low bandwidth network with very less distortion. You may have your phone or any of your communication devices will have its own codec, audio codec and video codec. The audio codec is called the speech codecs sometimes. And what it does is it's going to take the audio and then it's going to run an encoder on top of that audio to get some bit or some data which it can transmit over the internet or a network, and the decoder will be able to synthesize an audio using that the packets which it receives from the network. So think of this in this way. So let's say you have an encoder, right? If you have done digital communication course, you'll know what an encoder is. It's not like a neural network encoder. You have an encoder and you have a decoder, and in between you have a channel. And this channel could be an internet connection a channel. Basically, it's called voice over IP channel. Sometimes it could be a normal telephonic cables. Right. So there are different channels here, depending on the modality of the communication. So the encoder could be some DSP algorithm, right? So there are many encoding algorithms people have proposed based on the signal processing approaches. In the for many years, people have been using it, and these days these encoders are replaced by neural networks. We'll come to that. So this encoder, basically what it does, it takes the audio and then gives you some output, right? Some output, and those will be some kind of bits, right? So the numbers, ones and zeros, which you can transmit, and the decoder will know what type of data that is, and it's going to reconstruct the audio for you. So ultimate goal should be the audio should have very less distortion. It should retain the same content and preserve the speaker identity and everything without adding much noise or distortion during the generation. So this is the idea of speech codec, right? Speech coding. So, like I said, in the past, many algorithms have been proposed, and these days, lot of people, lot of varieties of codecs are available. So, for example, Opus, G711, there is LPC coding, then LPEC coding, then Speaks, and so on. So, there are many encoding algorithms available as of today, which you can use for your speech coding application. Now, this is all, like I said, all these algorithms I mentioned, they are all using some kind of digital signal processing algorithm, right, to the encoding to do the encoding and decoding. But what we are going to discuss today is, instead of using these signal processing algorithms, can we leverage a neural network to do the encoding for us, right? Because for many years, neural network have shown great promise in compression, right? So basically, you can use a neural network to encode audio or any other uh, data, for example, image or any other data And the encoded output, you can think of it as a compressed representation of the audio. And you can ask the question, can I use this compressed representation to recover the original data, right? So this is the question you can ask when you want to use a neural network for compression, right, or coding. In our case, in speech coding, I can say, can I use a neural network to encode an audio, right, audio signal, and the representation which I get from the output of the neural network, it can be low dimensional, right, and low dimensional in the sense it can have we can get as less information as possible, and can I transmit that small amount of information to the decoder, and the decoder should be able to reconstruct the audio using that small amount of information or small amount of data, right? So that's what we are going to see in this paper. So like I said, this idea people have been trying for the past 5-6 years, and they are thinking about how can we use these neural networks as an encoders or codecs, right, in the basically in the compression space. So in this paper we are going to use, or we are going to talk about this idea of using pre-trained transformers or pre-trained or self-supervised transformers for speech, and can we use those representations from these transformers and get better bitrate by maintaining the same quality in the decoded output, right? So what in this paper they propose to use two different or combination of two different types of encoders. So there's one convolution encoder which we'll understand, and we are also going to use this pre-trained transformer, which you can think of it as some kind of wave-to-wake or any other self-supervised model, right? So the paper shows that if you supplement the wave-to-wake features or self-supervised pre-trained models feature to the convolution encoder, you will get very good bitrate, like I mentioned, and it outperforms all the previous models or previous algorithms published for this space in speech, and also you get very good quality during the synthesis, right? And we'll see the results and the evaluations they are conducting for this paper in the coming slides. Now, let's understand what self-supervised learning is. Like I mentioned, in this paper, they're trying to use the self-supervised features or the pre-trained, the self-supervised pre-trained models features for the compression, right? So, for example, if you have an audio, let's call it as X, we are going to use this wave-to-wake framework, and this wave-to-wake framework will give us some contextual representation of the audio, which is of low dimension, and we can say this C or this contextual representation will retain a lot of information about the speech, and using this you can you can say we can transmit this contextual representation over the channel, and then reconstruct the audio, this audio, using only these features, right? So how this wave-to-wake model works? So as it's shown here, you have an encoder, which is some kind of CNN architecture, right? It takes the raw audio, it's a one-dimensional CNN, and it generates frame-level feature vectors, right? So these are called latent representations, Z, right? So for example, if your audio is 1 second, you may get about 25 frames, right? So this is our audio. This will be 16 kilohertz, and we are drastically reducing the number of samples. And this Z is fed to something called contextual network. Here it is shown as transformer network, and this transformer network will output something called contextual representation, which are again sequence of vectors. And the way the model is trained is by using something called contrastive predictive coding loss, and the contrastive loss, basically what it does is, or what it says is, I want to minimize the loss where, or you can think of it in this way, let's say you are at time step t, and you can quantize the z vector here, the zt, to something called qt, which is the quantized representation of zt. And then for this frame, I can ask the loss to uh, minimize the distance between qt, and we call this as ct, minimize the distance between ct and qt, but maximize the distance for all other samples, or they are also called distractors. So in simple terms, you can understand in that way. So when you train this model in such a way, you will get a good or good model, which will give you a meaningful feature representation. And as I mentioned, this transformer, you apply those kind of laws to the masked locations, right? Like for example, in this case, we are at time step t, and we mask that frame while feeding it to the transformer, and we ask the CPC loss to compute this CPC, or compute this contrastive loss for that frame, and we would do it for many frames here, right? So this is a completely um, this is a paper on its own. You can search for wave to wake 2.0 or wave to wake paper. It's a very big model, and it has its own explanation, and it has its own uh, ideas which you can understand from that paper. So I also have a tutorial on this paper. You can go and check it out. So this is how the self-supervised models are trained, right? So you have an audio, you have lots and lots of unlabeled audio data, and how can we leverage all of those unlabeled audio data to learn a good feature extractor, which can use it to extract features for downstream application maybe, or we can also use it for this kind of encoding or compression application. So now let's understand the actual paper. Like whatever I explained in the previous slide, it was just an intro to a self-supervised model, or specifically a wave-to-wake model, how it is trained, and how what is the advantage of using that model in this speech applications. So in this section, I'm going to explain to you the actual overall architecture of the proposed approach for this paper, right? And then we'll understand three different blocks in this algorithm. It's called encoder, quantizer, and the decoder. So the encoder. So let's understand the model architecture here. So as you can see, the model has two parts here. So this is an audio. This is the audio signal. This could be, it can be anything. It can be music, or it can be just an audio signal, right? It's a speech signal, right? So it has two, like I said, it has two branches. So one is called a convolution network encoder. Uh, it's also mentioned a sound stream here, because it's a this is some kind of this is an architecture or an algorithm which was published by this paper called SoundStream, which was published a couple of months ago. And this branch is combined with this pre-trained models, or pre-trained self-supervised pre-trained models, to see if you can get a better improvement. So baseline, you can think as the SoundStream model, right? It's a standalone SoundStream speech codec, right? And what we are doing in this paper is by combining or cascading this pre-trained wave-to-wake model to see if we can get any improvement over this previous baseline model, right? So so this audio, we can feed it to the convolution network encoder or a sound stream. So it's going to extract feature vectors for this audio, and those will be of 64 dimension, and the frame rate is 50 hertz, right? And which means there will be 50 vectors per second, right? And similarly for pre-trained transformers, you have 1024 dimension feature vector, which are extracted from the last layer of the context network, and those are running at 25 hertz, which means there are 25 frames per second, which means for every 40 millisecond we have one frame, right? And as you can see, each of them are some kind of feature extractor or encoders, right? And the outputs of those are fed into something called residual vector quantizer. So before going there, the pre-trained transformer output, which is of dimension 1024 at every frame, is reduced to 64 dimension using this dimension reduction module, which is just a simple linear layer of dimension 1024 to 64, which takes, that means it takes 1024 dimension features and reduce the dimension to 64, but the frame rate is kept as it is. This is to just add or concatenate the features here. That's all, just to make sure the dimensions of these two branches are same. So once you have this output here, which is the output from the encoder, let's call this encoder 2, and we have this encoder 1, and these outputs we can feed it to an individual separate vector residual vector quantizers for each, right? So we have vector quantizer, residual vector quantizer for the branch 1 or the convolution neural network encoder, and similarly we have residual vector quantizer for the pre-trained transformer. Now, what the residual vector quantizer does, it compresses or it converts this continuous representation to discrete representation, right? So basically, it's some kind of quantization model. It's a say the quantization models are also used in the old classical speech codecs, right? So they are like different types of quantizations, right? So just to give an example, there is an algorithm called Lloyd quantization, Lloyd. So if you do DSP course, you'll remember this algorithm's name, quantization, Lloyd quantizations, right? So like that, this residual quantization is also one type of quantization which basically quantizes the residue or the difference from the mean features, right? And it does iteratively using cascade of vector quantizers, and the output is finally transmitted to the decoder, and the decoder. So basically, this you can think of it as a channel, right? So this is a channel which transmits this data to the decoder. So for example, let's say you are calling someone, or maybe let's say you are watching Netflix, right? So this happens in the Netflix servers, right? So this is Netflix server. So Netflix server is going to take the movie, or let's say you Spotify, for example. Let's say Spotify. So Spotify is going to take a music. Let's say you want to stream the music. So they take the music you want to stream and they run it through this model, and whatever output they get from this, they're going to transmit to through the channel or through the network or the internet, in our case. And then in your phone you have the Spotify app. The Spotify app will have its own decoder, and the decoder will receive the signal, which are basically bits, right? Ones and zeros, and those ones and zeros are converted to audio stream which you can listen in Spotify, right? This is just an example. I'm not saying Spotify does this. They may be doing it, I don't know, but this is how you can think of this whole speech codec application, right? The same thing Netflix can do, or this algorithm was actually developed by Google's Chrome Media team, and this sound stream algorithm was actually developed by a couple of people from Google Chrome team, and also a couple of people from Hangouts team, because Hangouts is again a streaming service, right? So you can call a person, or you can have like a video conferencing and so on. So this is very important in such use cases, right? So this is the, like I said, this is the decoder, and the decoder will have some kind of vocoder. It's not really vocoder. Vocoder basically converts the spectrogram to audio, but in this case, it's called decoder. So the decoder is a generative adversarial network here. It's going to synthesize the audio, and then so the audio, ideally, the audio should be as clean and as good as the source audio itself, right? Then we can say we have achieved a very good, or we have built a very good speech codec. Now I'm also showing something here in the bottom. So this is basically the algorithm used in this sound stream paper, right? So this basically is kind of similar to this whole approach, but except you don't have the pretrained transformer here. So they have an encoder, it's a convolution encoder, and they have a decoder, and they have again residual vector quantization in the middle, right? So the input goes to the encoder, and the output is basically generated using the decoder from the quantized representations, right? And there is a discriminator, which is basically to train the model, train the decoder especially. And during inference time, what happens is you take the encoder, which is called a transmitter in the DSP terms, right? This could be your a friend calling you from his phone, and the audio gets encoded through let's take an example of Hangouts. So let's say you're calling a friend, and the friend or your friend is calling you. So he or she will transmit, or he or she will speak to their Hangouts app, and the Hangouts app, within it they will have this service running, right? So the service is basically a neural network which takes this audio and then gives you these ones and zeros, right? And these ones and zeros are transmitted to the channel, and your phone, which will have again a Hangouts app, and that will also have a decoder service, and which will take these streams of ones and zeros and then generate audio, which you can listen and interpret. So this is the model architecture, right? And so like I explained, the encoder basically generates two different types of embeddings, right? One from the pre-trained model, and one from the with convolution encoder, right? So, and the pre-trained model features are of dimension 1024, operates at 25 hertz, and the convolution encoder features are of 64 dimension and operates at 50 hertz. And the quantizer, like I said, they are using residual vector quantizers. It's a cascade of vector quantizers, right? And like I said, the residual is said because it quantizes the error from the mean. And those, and like I said, each uh, model or convolution encoder will have its own residual vector quantizer, and transformer also has its own vector quantizer. Now, decoder, like I said, decoder is a GAN, right? Generative adversarial network. It synthesizes the audio, which is spoken to the encoder at the start, right? And so the encoder, so generative adversarial network, as you know, will have a generator which will generate the audio, and there is a discriminator which will tell whether the synthesized audio or generated audio is real or fake, right? And in case of this paper, or in this case, they are using multiple discriminator just to make sure the generated audio is high quality and has a very good perceptual score, right? So they are using two different types of discriminator. One operates in time domain and one operates in Fourier domain, right? And the time domain one has three different time domain discriminators are of there are three time domain discriminators. So dk, so k could be 1 to 3, right? Each one operates at their own signal resolution. Like one could be, let's say, will have like basically so they say they operate at subsampled by factors of 2, 4, and one is the original signal, right? There are three discriminator. One gives you the original signal quality or original sampling rate. Another one gives half the sampling rate. Another one is 1/4 of the sampling rate, right? So they are like basically generating audio at different resolutions, right? And also this helps. I mean, they claim that this helps the model to learn speech signal at different time scale, so that we can have a better perceptual quality. Now, coming to the training, like I said, there are many blocks here. So there is convolution encoder, there is generative adversarial network, and within that there is generator and there is discriminator, right? So so these are like they use many loss functions, right? So in this loss function, so the theta is basically the convolution encoder parameters, right? So they're using this is expectation, and they're using three, like I said, three or four discriminator, three for time domain and one for spectral domain, right? sorry, three for time domain and one for MS, Fourier domain, right? And this is the loss function for that, and there is a GAN loss function, which is expectation of the discriminator and the generator. So this is a standard GAN loss, right? And there is a feature loss. So the feature loss is basically calculated at every layer of the convolutional encoder, and there is a reconstruction loss to get reconstruction loss basically makes or reconstruction loss helps you in getting a smooth spectrum, right, for the audio, right? And there is one more loss here, the quantization loss, right? So I mean these losses are explained in detail in the paper I showed you. So the stream this paper, sound stream paper, right? These are explained in detail. If you want, you can read the paper. Also, I am also planning to make a tutorial of this sound stream paper, right? And in the future, right? So at the end, let's see the experiments and results. This is what we have been waiting for. We want to see how much improvement we can get by adding this pre-trained self-supervised model, and what happens if you use just the pre-trained self-supervised transformer or self-supervised model alone. What happens when you combine both of them, the convolution encoder and the pre-trained model together? So there are two different metrics they are showing here. So one is called VSCOL. So this is actually a metric which was proposed by the same team 2 years ago, and there is another metric called WarpQ. Again, it's the same metric same team proposed this metric as well to measure the quality of the codec, right? And these are neural network based approaches. So you can read these papers in details. So basically, what you can see here is that if you use only the transformer model, the bitrate for lower bitrate you get lower score. This has to be higher if you want the model to be like a speech codec to be better, right? So if you see this combining the transformer and the CNN together will give the best score both in the lower bitrate case and the higher bitrate case. Similarly, WarpQ, this has to be lower if you want the codec to be better. And if you increase the bitrate to 1.75, as you can see, combining these two models is better than using each one of them separately. And in the end, we'll see this another plot which they have, which is basically what is the quality or the perceptual quality of the audio. So Mushra score basically tells how good the audio quality is, right? And as you can see, even in the lower bitrate case, you have transformer plus CNN having a very good Mushra score compared to the classical old codecs such as Speaks and MLLP or MLP or LPCnet, right? And that means using these models, you can transmit data even with very low bandwidth, right? So 0.4 kbps, even with very low bandwidth network, you can get very high quality audios, or you can have speech codecs which will generate very high quality audios, right? So this is kind of a revolutionary thing, right? So in the past, we were stuck with these DSP algorithms, and there was a limit, and we were we had to have some kind of or we had to have a good network connection in order to get good quality audio. But with this invention of this neural network and these algorithms, we can have like very low bandwidth network, right? And with such low bandwidth network, you are getting very high quality audios or high quality data, right? You are able to transmit such high quality data. So this I think will revolutionize the streaming, the way the streaming applications are built, right? Like for example, like if you see Spotify or Netflix, right? So you can watch those movies without any buffering, um, with without any buffering, in high quality, even with very bad internet connection, right? So I think maybe in the future, I believe all the communication companies or all the streaming service companies will change their codec codecs to this neural network. I hope they all change their codecs to this neural network based codecs, at least in the future. In a couple of years, I believe this will become very big thing. So with that, I'm going to stop here. Thank you so much for watching this tutorial till the end. If you like this tutorial, please give a thumbs up. If you want to watch these kind of content in the future, subscribe to my channel. Thank you.